Yeah, so today we're talking about fluid transducers. We've talked about how to model fluid and thermal systems now, and that's great, but oftentimes we're going to work with systems that have multiple energy domains associated with them. So that's why we'll introduce fluid transducers today, and we're also going to talk through an example as well. So it's going to be good. So fluid transducers. Although thermal systems often exchange energy with other energy domains, it is much more common to consider those systems that interact with thermal systems to be generating or sinking heat. So generating or sinking heat, often modeled as a dependent source, than to see a proper transducer. This is associated with thermal systems, thermal energy being sort of the highest entropy form of energy. So entropy is always increasing globally. So that's in part why this transduction doesn't really happen in a proper sense for thermal systems. But fluid systems, there's a whole lot of transducing sorts of mechanisms that we have. So fluid systems, on the other hand, very naturally interact with mechanical systems. For instance, piston-cylinder mechanisms. So on one side, you have a fluid that's, say, maybe generating a pressure that's pushing a piston that moves something in a linear fashion. Or you could have the piston driving the fluid. That would be one example. Propellers, turbines, and impellers, which are just backward turbines. There's just a few energy transducing elements. So these are very commonly encountered in mechanical engineering, these sorts of systems. So these systems are often driven by motors, for example, a pump's impeller, or drive generators, for example, a dam's turbine. Therefore, it is common to require a fluid electromechanical dynamic model. So these are blue. Oh yeah, I was going to ask you guys on the video. I noticed in the last videos that there were like cuts, like 1 second or so would be cut out. Yeah, is that always like that, or is it just? Yeah, I don't know what was going on. There were some weird technical things happening.
I thought you were doing it on purpose.
Yeah, like cutting. Just like it's like my YouTube, I cut out all the dead space and this, yeah. Except for DJ now, it just reminds me of DJ TJ. No. Everything's tainted now. Nothing is sacred. So let's do an example. A micro hydroelectric power generator. So this is fun. Dams, even small micro dams, generate hydroelectric power by directing water through turbines, which rotate, creating mechanical power and drive electric generators, generating electric power. For large-scale dams, the flow rate is regulated, so this is a common setup, such that an AC generator produces a nice 60 hertz. So if you have the flow rate regulated, you can spin the turbine, spin the generator, so that your AC generator generates at 60 hertz, which is the power grid frequency. So that's what you'll often see. You don't have to do anything to it. It's just ready to go. However, micro hydroelectric generators typically cannot expect well-regulated flow rates. So sometimes they use a brushed DC motor, or a DC generator, which is just a DC motor backwards. The big disadvantage to doing this is that when you use a brushed motor, you have to replace the brushes. So if you use it, that's one of the primary reasons why they prefer to use AC generators, is that you don't have the brush to replace. So assuming a micro hydroelectric dam can be set up in a manner similar to a large-scale dam, draw a linear graph model from the following schematic. So I showed a hydroelectric dam, and this is a really nice figure from, you guessed it, Wikipedia. Yeah. Actually, somebody at some Tennessee water thing made it and uploaded it to Wikipedia, and the rights are pretty open, so as long as I cite them, it's good. So it's pretty cool. I like this figure. So there's the reservoir, and then there's an intake to the penstock, which notice there's a drop in elevation there. Drives through the turbine out into the river below. The generator is being turned by the turbine, and that generates the power, electric power. So let's draw a linear graph to model this situation. And actually, lecture 4.4 is taking that linear graph and then turning it into a state space model. So yeah, this is like your first day on the job. You got hired by some either engineering firm or maybe a state authority for hydroelectric power, and they're like, model this for me. And you're like, sure, no problem. I can do that. Dynamic model, do some simulations. Got this. So, this is, let's just step back for a second. This is a great example of the type of system that a complex, detailed fluid dynamics model is not what you want, okay? If we're interested in like how much power is going to be generated, or if we're interested in like what the flow rate's going to be coming out of this output here for a certain height in the reservoir, a complicated fluid dynamics model isn't going to get you there. It's just not the right model for this. So this is the type of system that we would want to use, or the type of analysis of the system we would want to use this system dynamics approach for. Now, if you were interested in optimizing maybe some aspect of how this water flows around the turbine, then you need some really complicated, like probably computational fluid dynamics, CFD model, COMSOL, something like that, where you're trying to say, okay, the geometry here we could tweak so that we get a little bit better efficiency out of it. Like that's the sort of thing you would need the fluid dynamic detailed model for. This large-scale system-level thinking, we would want to use a system dynamics approach. So this is this is the part that's we often gloss over in these classes, but I'm trying to slow down and help you guys get some intuition on it, because the rest of it is pretty much a recipe, right? We go through the recipe. But this high-level stuff where you're thinking, what type of model should I use for this? That's the part that is really hard to get somebody who's good at doing that. So that's why we talk about it here. So let's first talk about like the different elements that might show up in this. The first obvious one is there's this big reservoir, right? That's like where we're going to get the power from, by letting some of this reservoir water flow through. Now, this has a pretty significant, hopefully, if it's not an empty reservoir, a pretty significant head, right? So that's the potential energy that you're going to get, and so that looks like a fluid capacitor, right? Okay, so any like tank or reservoir of water, you're thinking, oh, it's a capacitor. And the intake here is probably going to cause some resistance to happen, right? So thinking like capacitor, thinking resistor as it goes through there. There's going to be, some, it's hard to say from the diagram, but there's going to be some head here too, right? So the pressure down here is going to be higher than the pressure up here, so we should take that into account as well. And that's another capacitor. It's going to flow along this. It looks to be, you know, we can assume that it is a relatively long, narrow pipe. So we could say this is probably a resistance and a inertance, right? Along here because it's long. So anytime you flow through anything, you're going to get a resistance. So resistance, and then the inertance arises from having it be long and thin. And then it's going to go through this turbine, which is going to be the transducing element, right? So it's going to have, it's going to generate some mechanical rotational energy here. So transducer. And then on the mechanical side, we have like, you know, there's going to be some rotational inertia, and there's going to be some damping from the bearings. And then you've got the generator model too. Generator model, which is, we have a DC, brush DC generator, so it looks just like a brush DC motor. Sidebar, AC motors are harder to model dynamically, so it's not that they can't be modeled, but it's just harder. So that's part of why we're using DC in this example. And then on the output, we've got some resistance, and it doesn't look like it's as long, so we'll just say there's going to be, you know, some head here, and there's also going to be some resistance. Okay, so there's a lot going on, right? But let's see if we can just sort of take it one thing at a time. Oh, and then you got to assume that this reservoir is being fed by something, right? So probably some, you know, the runoff from rainfall or snow melt or whatever's feeding the reservoir. So you've got some source coming in. Okay. Oh, I did want to mention here too. So the I said capacitor for this, but actually this is a probably better model instead of a capacitor would be to model it as a so it's we often just write head here. So this is a pressure source. You know, anytime you have a pressure drop like that, that's constant. It doesn't change. It's just due to the geometry, right? This is just always going to be there, that pressure drop. We would just say this is a constant pressure source. It's always going to be the same between these two. So there's that, and then the same with this pressure drop. Okay. So let's try to draw a linear graph of this. So this is all, I mean, there are different interpretations you could make, but this is decent. Yeah?
So I have a question.
Yeah.
So you said since it's long way, so we're adding the resistor and the IN to it. So how long is supposed to be considered as long?
Yeah, so if you'll recall, I think that the inductance, the inertance parameter for a pipe, we derived it in the lecture, I think 4.1. And it had the, it had L divided by A in it. And then there was another factor here. I think it was rho. And the L is the length that it flows through, and A is the cross-sectional area. So the longer it is with the less cross-sectional area, smaller cross-sectional area, means higher inertance. If it's relatively large area, if this is big, and the length is short, then it's going to be a small inertance. So it's always just a sort of judgment call as far as, do we need to take this into account or not? It's going to be there even if you have a short, wide pipe, but it might be negligible. It's like, oh, it's not enough to really matter. We won't worry about it for this model. In a model that you're really concerned about all of the details with, you might want to include it in any case. But a lot of times we won't include it unless this parameter is significant. So you can always compute it and try to get a feel for it. And a lot of times the way to go is to say, okay, is this significant in comparison to other inertances in the system? Like maybe it's a factor of 300 smaller than any of the others. You say, oh, okay, we probably don't need to worry about it. That type of thing. But it is a judgment call. And sometimes it's best to keep it in there at first and then later on say, oh, this is not significant. We can reduce our model down and just get rid of this. So it makes the modeling a little bit simpler when we ignore it, but you got to be careful with that. Sometimes it'll bite you. So, okay. Let's start out kind of on this left-hand side, and let's model this. Let's model the fluid aspect completely, and then we'll move on to the mechanical and then the electrical. Okay. So, the fluid side has this capacitor, and it's got this flow source feeding the capacitor, right? So let's start off over there. Let's establish a fluid ground. And that fluid ground, let's say, is just P atmosphere, okay? Atmospheric pressure. That would be our reference pressure. And the capacitor, the fluid capacitor, is going to reference that. So we're going to call this C1 because there are going to be several capacitances in this problem. And we've got a flow source that's feeding it, right? So a little sidebar on signs, because we haven't talked about signs this term. The thing you can always fall back on is that whatever direction you draw your arrows is fine as long as you go back and try to interpret it with that arrow direction. Just like when you did free body diagram and you didn't know the direction of a force, and you just drew it one direction, then your interpretation has to reflect that. If it's negative, it's actually going the other way. You can get there's more involved sign conventions. One thing you have to get right is that the source has to be the correct sign. So the flow source here is flowing into that capacitor. We would want that to be positive going in, and not have to say like, oh, this is a negative flow. That would be weird. So you got to get that sign right. Everything else you can just kind of draw whatever. So, okay, so you've got your flow filling this capacitor, which is great. We're going to use that. We're going to flow out of this capacitor through this resistor into this pipe. So we've got through a resistor, we'll call R1, and then there's really no better order for this. You can choose any order you want, but let's say there's an inductor neck, or inertance, I should say. Sorry, it's the generalized inductance, and so I start to say inductance sometimes when I mean inertance. So there's an inertance, there's another resistance, R2, and then we have to model this pressure head. And like I said, so unlike the reservoir can change heights, right? if it was a constant height reservoir, we could model it as being a pressure source. But since it can change heights, we model it as a capacitor. This one, the head is never going to change between this location and that location. It's always going to be the same. So you would model that as a pressure source. Okay? So this is a pressure source. And in order to, so I'll call it PS1, because we're going to have another one. The sign on this, I'm going to put that way because what that says is the pressure drops from this node to that node, which is correct, right? So the pressure is higher here than it is up here because it's at a lower elevation. So you got your lower elevation underwater, you're going to get a higher pressure. So the pressure here is higher than it is here. Okay. So we've gone through the penstock, and now we're going to go through this turbine, right? So the turbine, we're going to model this as being a transducer. So we're gonna put this interface branch right here, ready to go, and we'll call this branch 1. We're going to interface with that with the rotational element from the turbine, but we're not going to do that yet. We're gonna finish off the fluid side first. Yeah, go ahead.
Would it be common to put on pressure source to put a circle around the arrow indicating it's a source?
Oh yeah, good call. Thank you. Yes.
I just wanted to do it where it was normal.
It is. It is. We all try. Some of us are not as good at it. So, okay. And then after this, you've got this pressure head again to go down to this outlet, right? So there's another pressure head that you go through. So let's draw another pressure source. And this one is going to be lower here, so it's going to drop that direction. So, yeah. So this is PS2, my last gaming console. Yeah. Before I had no time to play video games anymore. That's sad. But something to look forward to when you're like old in a nursing home, probably video games again. So something to look forward to. Okay. Or young in a nursing home. I don't know how you live. I mean, okay. So this is another pressure drop. And then also we're going to say there's a resistance here too, right? There's a resistance, probably not an inertance. So we are probably going to go like that. I didn't really plan that very well. Obviously, I forgot my notes, so we're just doing this. And we'll draw it that way. This is 3 now. Okay.
Would we not model the capacitance of the river?
Oh, thank you. Thank you. That's what I'm forgetting from my notes. So the river's got some head too, right? But it's not just a stationary one. The level changes. So we got to model it as a capacitor. Good call. Thanks. It's like, God, that doesn't seem right. There's something wrong. All right, so we've got a resistance, R3. But then we've got a capacitance here, right? And so we've got C2, because this pushes back, right? River's got some head as well. I think the one that we're going to use in the next lecture combines R1 and R2 together, which is totally legit. They're in series resistors, so you can just add them together. once again, didn't bring my notes. But you could do it either way. You could either model this resistor as one resistor and this one as a separate resistor, or you can combine them to make one R. Okay. So we've got the fluid side down. But now we've got to do the transduction into this mechanical system. We're turning the turbine, and so we interact with the fluid side through this transducer. And the 2 side has got, on the mechanical side, you got to think, okay, well, we're turning a shaft. The shaft's got to be on bearings of some sort, right? So that's going to introduce some damping. It's going to also turn a rotor. I mean, it's going to have some inertia associated with it. So there's going to be some moment of inertia. So I'll put a moment of inertia, J, and then also a damping, B. And then what does it do? It interacts with the electrical side through the magnetic field, right? So, and this is, of course, the mechanical ground, which we would say, like, for instance, angular velocity equals 0. This is the angular velocity equals whatever it's spinning at, right? Okay, so we've got another transducer that goes from the mechanical rotational side to the electronic side, right? So it's got to interact as well, and we'll go to ground here. So this would be ground would be voltage equals 0. Now, these 2 interaction branches we'll call 3 and 4. Now, we're saying this is a DC generator. So a DC generator looks just like a DC motor. Okay, so we're going to have the coil resistance. So what are we now? R4? And then we've got a also the inductance of the coil, L1. And then typically, so if it was a DC motor, we would have the voltage source, right? But we're not going to have a voltage source. We're going to have instead, we're going to have some sort of a load, right? This is the, this is the payoff right here. We're going to flow water through, and we're going to have energy flowing this way, right? From the fluid system, through the mechanical system, to the electrical system. And now the question is, what are you going to do with this stuff? That is actually like half of the problem when you generate electricity is what are you going to do with it? Because as you generate it, you got to do something with it now. And some systems, like a micro hydro stuff, it's not super sophisticated, and they just literally just dump energy sometimes if you don't have anywhere to put it. If you charge up, say like your battery or whatever, the water's still coming through, you just start dumping the energy. So what we'll model this as is say this is a micro hydro and you've got like this, you're damming like a stream that's like out like a property or something like that. You're damming a stream, which I don't know the legality. I'm just saying, say you were doing this, and you were harvesting energy and you were powering like one of those home batteries that. What's the batteries?
Will you use them for like solar panels when you can sell back the electricity?
Yeah, totally. I was just trying to remember. There's a whatever Elon Musk's battery company is called.
Tesla.
Well, it's the Tesla.
Isn't it like solar smart grid?
It's something. Yeah, I don't know. Whatever it is. Anyways, he's got some like home, like big battery that you can charge up during the day using whatever, like wind or solar or whatever you've got. and then it'll allow you to power your home all night with it, and then yeah. So part of the problem with a lot of these nice energy harvesting methods is you don't know where to put the energy while you don't need it, and then you need it later. Where you're going to get it. So the charging up a battery is a pretty reasonable assumption with a microhydro application. So we'll do that, and we'll model that as being. There are different ways you can model it. I'm going to model it as a capacitor. So model it as a capacitor. So this is C3 and a resistor R5. And the reason that I'm putting a resistor in parallel there is that your battery is going to, just like with the capacitor you guys modeled in I think it was your last homework, there's some leakage, right? So you're not going to be able to store this in a capacitor indefinitely. Also, you're going to deliver to a load too. So this could be, you're actually like running your lights or whatever. That could model the load you're drawing. You might want to model the whole electrical system and its demands as well, but we're not going through that detail at this point. So you can deliver power though. So you can store it in C3 and you can deliver it to R5 if you use that as your delivery resistor. Okay? Now, this is it's a pretty complicated model, but I claim that this is, for you guys, like no harder than a second order system. It's just more of the same stuff, right? If you had like only the reservoir and the drop here in the river, it wouldn't have been that hard, just the fluid side. Or if you just had the mechanical side, that would be pretty simple. Or if you just had the electrical side, it would be pretty simple. But you have them all together, but that doesn't faze you because it's just more of the same stuff. You just can methodically, systematically go through it. So, any questions on the modeling aspect of this? So going from this sort of concept, this reservoir, penstock, river, turbine, generator, we got to this, and then we're pretty much, the rest of it is just coasting downhill on recipes, right? Once we have this drawn, we could write a computer program, take this graph, and generate a state space model for us. Yeah?
Can you go over again what the mechanical side with the 2 and 3 comes from?
Yeah, so the mechanical system is pretty simple. It's just a rotational mechanical system. It consists of a shaft, some bearings, and then some, inertia that turns. So you're probably going to be turning a rotor that's going to have some significant inertia you need to take into account. So the mechanical system is pretty simple. It's really just one rotational speed besides the reference of 0, so 1 omega. And then you've got 2 interactions, though. You're interacting with the fluid system through the turbine. So that's what the 1-2 interaction is describing. And then you're interacting with the electronic system through the windings. So the 3-4 is the interaction with the windings. Yeah. So it's pretty cool. And I think that what I'll do is, okay, so we'll finish. We'll just end this lecture. If there are no other questions. Oh, there are other questions. Yes.
I'm wondering where the pressure versus P sub S1 and S2 come from.
Yeah, so PS1 and PS2, they are modeling these 2 constant heads that we have in the system. So we've got two different heights here and here that this pipe flows through. So we recognize that when you're at 2 different heights, the hydrostatic pressure is different there. So we can model that. If it's a variable height, we would model that as a capacitor. But since this is a constant height, we're just going to model that as a as a pressure source, because it is just going to change the pressure. The pressure from here to here is just rho GH, right? It's just that constant pressure head that you get from the difference in height.
And that's different than the initial head that the water comes in from?
So this, so the head that you get from here to there, we're modeling as a capacitance because we're saying that this height can change.
Okay.
The reservoir, we want to be able to model it changing height and how it affects the power generation.
Gotcha.
Whereas the geometry we assume is never going to change between this height, intake, and then where it hits the turbine. And then it's the same with this. There's a head difference there. That one's less significant possibly, but it's probably good to take it into account. And so these are modeled as inputs, but they're constant inputs. They're always the same. So.
And for the electrical side too, so we just have to assume the R4 and the inductance and all that. Because there's nothing really modeled up there on the actual picture of that too. So.
Right, so we're just basing this off the knowledge that I said it's a DC generator. So a DC generator is going to look something like this. For an individual generator, we would have to know what its winding resistance is and also its inductance, which are spec sheet things you would be able to find or measure as well. And then C3 is going to depend on however you store it, so whatever the battery is. And then R5 is going to be, delivering a load to your system. Or if you're just storing all of this, then it's going to be some leakage that's going to happen.
So if you're just storing, could it just be C3 or does it have to go to R5?
R5, if you're just storing it, R5 would be there to model just like the fact that if you charge up a battery, it slowly is going to discharge, and that would be modeled by R5. Or you could use R5 to model the load, or you could do two separate ones: one to model the slow leakage, another one to model the load. Yeah. Okay. Any other? Yeah.
So if the head went the other way instead of dropping down and went up, that just changed the sign of the pressure?
Exactly. So if you had say your turbine was at the low point and your outlet was higher than the turbine, then we would change, and you could just change the sign of your input pressure. Probably would be better to just actually flip the arrow so that the head is clearly going the other way. It's just making sure that when you draw the graph that you recognize what that means in terms of the physical system. And usually when we draw a source, we try to make it draw in the direction that is the most physically interpretable, I guess. So yeah, but you're right. If the head went the other way, if the turbine was at the low point and you went back up to discharge, then the head would be pressing against the other way. And we want water to want to flow down and through all this stuff, which is part of why the head is dropping here. So the pressure is pushing it this direction. It's part of it. Of course, with this, you're going into the river, so this is pushing back, right? That capacitance of the river is pushing back. If you ever ended up with a situation where the river was higher than the reservoir, it'd be big trouble. It's not what you want. But yeah, that should never happen. If that happens, it's probably the least of your problems. There was a tidal wave coming up the river. So what I'll do is, we have class Friday technically, but I'm gonna be giving, it's Engineering Awareness Day, so I'm gonna be giving presentations. I don't exactly know what yet. If anybody wants free tickets to an engineering banquet, let me know and you can help me do the presentations. I don't know what I'll have you do, but it's just gonna be a bunch of high school kids coming, and it's usually fun. I usually just stand up there and just talk at them for a while. And then, so I'm doing that, so we won't have class, but what I'm gonna do is, lecture 4.4, this is lecture 4.3. Lecture 4.4, I'll record, it's just an example of taking this and going to state equations. And so it's all the fill-ins are there. I gave them to you guys, so I'll go through and record a video of it, but that'll be the end of the lectures for this week. So, all right.